Welcome back, everyone. Now ready for the second part of this breakfast seminar, where we're moving into a bit more detail, starting with Vasileios Mavroeidis, who's a research fellow at the Security Lab at the University of Oslo, here with the help of Kamer Vishi. And when we were setting up this program, I just have to say I was emailing with Odin and Vasileios, and I discovered they were in the USA, discussing standardization of threat intelligence with NSA and others. So they're right in the middle of things, it seems. Now, as I said, moving a bit more into the details, we'll start with looking at machine-to-machine communications for cyber defense. So, here you go.
Thank you very much. Good morning, everybody. Today we are going to talk about the cyber defense of today and the cyber defense of tomorrow. Traditionally, every presentation starts by giving some insights about the present cyber threat landscape. We are not going to do that today, but to make the long story short, threat actors are getting more sophisticated day by day. They have more resources, thus higher capability, especially if we are talking about nation states. They implement new tactics, techniques, and procedures that are difficult to detect, analyze, and deter. And thus, the job of an incident responder and a security analyst is difficult. This comes in addition to that defenses still are statically configured and they operate in isolation. And the cyber response time is slow. So if it is to improvise right now and bring a threat scenario, a spear phishing attack. We are an organization, we are targeted by a spear phishing attack. We don't know it yet, so we got an email. We are not sure about this email. We have an indication that it may be malicious, so a security analyst would have to investigate it. So what would be the optimum solution would be we get the email, we decompose it, we check the headers, we check the sender, whitelist, blacklist, the domain, the content of the email, lexical analysis, the syntax, the language, the vocabulary in the email. What about if there is a URL embedded? We would need to investigate where this URL resolves to, which IP. Is this malicious? Is it non-malicious? What about if we have an attachment in the email? We would need to take this attachment, push it most probably to a sandbox, and then would have some behavior analytics there to understand of what's going on. Maybe this attachment, if we open it, would try to connect to a command and control server, to a specific IP, to a specific domain. Okay, so nowadays we're talking about automation and orchestration. So analysts and incident responders are trying to automate these tasks by creating some scripts, and then the whole point is that these tasks need to be part of an orchestration process. So maybe the result of the second task of an analyst needs to be fed in the third technology. Okay, let's say, for example, for the email attachment, the output of the sandbox would need to be fed. Maybe if it is malicious and we know that this attachment is trying to communicate with a command and control server, okay, maybe we could force our, maybe we could force a firewall rule automatically, dynamically to our solutions, okay? Any kind of solution, any kind of vendor. So another problem is that in our present situation, organizations have so many appliances, so many different firewalls, intrusion detection systems from different vendors. This would require you to have expertise for each one of them. So if you have a semantic firewall, a Trend Micro, a Cisco, or whatever, this would require to know the syntax of these firewalls if you want to implement rules, or would require to actually go to their web-based solution, to their application to do this, or to use their API, or to connect remotely and submit some commands, okay? This is an orchestration process, so the cyber defense of tomorrow would require to have these things dynamically configured and to be part of an orchestration process. So we're talking about coordinate defense in cyber-relevant time. So the incident responder would need to do, we have an incident, we need to answer back, we need to respond to this incident. This takes time, and most of the times these responses need to be coordinated. Some responses need to be in cyber-relevant time. They are more important than other responses. Okay, how could we achieve that? that would mean that each solution, each language that we speak, each solution would require to speak the same language, okay, to make it in cyber-relevant time. So if we are McAfee, if we are Semantic, if we are Cisco, we would need to have an interface that would be able to understand the same language. Okay? If we do this, then we can push any kind of command to any kind of appliance from any kind of vendor in cyber-relevant time. Okay? And this is what OpenC2 does. My microphone is the worst that can be. I'm playing my ears like all the time here. So if we go to explain what is OpenC2, it's a language that was initially developed, was initiated by NSA. And now it has more than 130 members. Many organizations are helping on this effort right now. So what is OpenC2? OpenC2 is, playing with my ears again. Okay. So OpenC2 is a language, is a suite of specifications, a language that allow us to command and control cyber defenses. In reality, any kind of system that operates in the network layer, but now we're talking about security. Cyber defenses then. The most important thing, it's agnostic of the underlying technology. So it doesn't matter what kind of vendor you are. If you are able to speak OpenC2, you can be orchestrated and automated. Right now we have three specifications. The language specification, which is the standard thing. It includes everything related to OpenC2, plus the rules that if you implement OpenC2, you would need to comply to some rules, the conformance. Okay? And then if we take a subset of these rules, we create profiles specifically for each solution. What do we mean by that? So if you have a firewall with stateless packet filtering capability, you would need to comply to the stateless packet filtering specification. Why? Because then we aid interoperability. You can communicate with any other technology. Okay? Because they know how to communicate with you. It's like communication protocols. Third, HTTPS transfer specification. Protocols for communication. OpenC2 right now can communicate over HTTPS. So if we move on, OpenC2 at a glance. OpenC2 is an unambiguous machine-to-machine language. It's very simple. It's actually in JSON format. It's very easy to understand, very easy to read. And it introduces low overhead on the sensor and the actuator. I'll explain in a while what an actuator is. So low overhead in the communications as well. Okay? And it focuses on the acting portion of cyber defense. This means that in order to issue an OpenC2 command, you need already to know, you need to have an action, what has triggered this action, okay, sensing, what triggers the action, analytics, context, why, what's wrong here, why do we need to issue some actions. This can come from cyber threat intelligence, we'll come back in a while, and then decision, which action, for example, deny this IP address with this destination port to this device. And this is what OpenC2 does, the action itself. So we need to have technologies before that to identify what's going on. Some terminology. We all need now to speak OpenC2. We need to understand each other, so we need some terminology here. Actuator, the device or sensor that executes a native OpenC2 command. So the firewall itself, for example, it's an actuator. Any kind of device that supports OpenC2. Okay, we can call it also consumer. So an actuator is a consumer. It takes the command. Okay, it consumes the command. Orchestrator, the device, the entity that sends the command. The device, the entity that produces the command. So an orchestrator sends a command to an actuator. Okay, a producer sends a command to a consumer. Profile, I explained a while ago. Stateless packet filtering profile, so subset of commands for a specific purpose. We create different profiles. So in future we'll have different profile for intrusion detection system, different for profile for endpoint detection and response, anything. OpenC2 proxy provides the mapping of OpenC2 in situations that the devices, the appliance, don't support OpenC2, which is the present case. Most of the devices don't support OpenC2, so we need something in between that will translate OpenC2 to the language of the appliance. So if you are Palo Alto, you have different notation syntax than Cisco. We have something in between, a proxy that translates. And this is the architecture. Nothing is absolute here. These are just examples. So we have the orchestrator, produces the command, and here, I can use the pointer, and here we have an appliance. So green line, it means that we have a native OpenC2 profile. It means that this device, the vendor itself, supports OpenC2. They can understand OpenC2. Okay? What about the cases that we don't have this? Yes? Good. OpenC2 message fabric and OpenC2 proxy. This doesn't make anything. They are just layers of abstraction. They could be both in the orchestrator. So the orchestrator sets a command. These devices here, Cisco, FortiGate, Palo Alto, Barracuda, Sophos, and Checkpoint, don't support OpenC2. Okay, different technologies. But we have the analyst and the incident responder that they need to push commands into all these different devices. If you are in an organization, most probably you'll have different firewall solutions. You don't have from one vendor because, for example, if today we have a zero-day exploit, you wouldn't want this zero-day exploit to affect all your devices, all your firewalls at the same time. So the incident responder would have to configure all these devices separately in a situation, okay, in a malicious situation. So we have the OpenC2 proxy there that takes the command, no matter what the command is. It may be allow, deny this, update this, a configuration file for the firewall. And then it translates the command to the appropriate technology. We have a device manager, then it knows exactly where it needs to push the command. The analyst has only to know OpenC2, nothing else anymore, and have some domain expertise, of course. So we can move on. CTI plus course of action equals automate course of action. CTI plus OpenC2, it also adds orchestration in addition. Why? What is cyber threat intelligence in reality? So we always used to share cyber threat intelligence, but nowadays we are trying to do it in a structured way. So we have what is known as intelligence feeds, which is in structured way, and then we are trying to extract things from these intelligence feeds. It may be written in XML or JSON format. Okay, a famous one is sticks, for example. So if we use sticks, it's a structured language for sharing cyber threat intelligence. Automatically from there, we can extract this intelligence. And for example, in the incident that we described before with the email, if we knew that this email is malicious, we would have to note down all the behavior of this attack from the entry point to the exit point. And then anybody else can use it. You can share it. Anybody else can have this knowledge. They can use this knowledge. Courses of actions, though. So in these intelligence feeds, you would have, for example, maybe the hash of the executable that the email attachment, conducted the command and control server, it download an executable that will do bad things in your computers. We can have the hash of this executable. We can share it. You can block it automatically. But most of the times in incident response, it's written in prose. So I'll need to go faster, right? So in incident response, these things are described in prose. So you would need to do this. You would need to block this port. You would need to correlate this with this to identify this. And then you would mitigate this solution by doing this. Okay? This takes time to implement. The incident responder would need to read these reports, to understand these reports, and then to be able to communicate with so many different technologies. Honeypots, sandboxes, intrusion detection systems, firewalls, antivirus, anything that you can imagine, endpoints. Okay? By introducing OpenC2 into the CTI fields, OpenC2 is structured. It's in JSON. We'll see an example in a while. So it means that the analyst can understand immediately the situation, what's going on, what do they have to do, and they can push these commands to the actuators. Okay? Another case is that you are an organization and you trust your parent organization or your security vendor, and they provide you with intelligence feeds. You don't even need to check anymore if there is a level of trust. Okay? You can consume these commands automatically. They can push them to your appliances. Okay? And this is again the same diagram. We're just showing that we can absorb cyber threat intelligence with OpenC2 in a structured way. And some syntax there because I'm going to show you an example. Action the task or activity to be performed. So, in the JSON format for OpenC2, we have an action, and the action may be allow this, deny this, update this, scan this, locate this. It depends on the situation. Okay, we have a target, which is the object of the action. For example, an IP, okay, a file name, a path, protocols, ports, anything. And then we have the actuator itself, which is the device that is going to perform the command. The firewall, let's say, okay? And some arguments and specifiers which add additional precision to the commands or the actuators. I'll show you now what I mean. Can we move on? So, this is an OpenC2 command. What we are saying here is, deny something, action deny, and the target is this IP object there, okay? Source address, destination port, and the protocol itself. And we have some extra arguments there. It says start time. This is the time that we are going to submit the command. This is the time that the command is going to be performed in the actuator itself, okay? And the time period, the duration of the validity of the command, this needs to go away after this time period. And we also ask for response back. Status 200 means that command was successfully implemented. So this is generally OpenC2, what does it do, and now my colleague Kamer here will demonstrate the use case, how I would use OpenC2 in reality. Okay? I'll sit here. Thank you.
Thank you, Vasileios. Is the mic working? Thank you, and hello, everybody. I'll try in a few minutes that has left to explain you a demonstration that we have developed. It's about translating the OpenC2 commands to the Cisco language. And it is a library. And I have a bad news and a good news. The bad news is that the tool is not available online yet due to some administrative issues. But the good news is that I'm going to give you a slide-based demonstration that is working 100%. Okay. At the beginning, OpenC2 community started to use a JSON abstract schema. But now we have taken it a step further using JSON and ASN.1 encoding, and we have introduced now G8DN, which stands for JSON Abstract Data Annotation, which is the reason why we are doing it, because the G8DN, it's a platform independent, so it means that even if the commands, OpenC2 commands, are on a binary format or JSON standard or on any other standards that are not available today, we are able to encode it and to decode it. The first thing that the orchestrator, as Vasileios explained, does, it sends an OpenC2 command to request a schema from the actuator or from the consumer. The action of this command is query, and then the target is the schema. So, sorry, I have to. The schema looks like a tilot. Okay. This is the schema that we get from the, or actually the orchestrator gets from the actuator, and it's in a JSON format, and it's include. This particular schema is for stateless packet filtering, and it includes all the keywords that we are able to construct an OpenC2 command.
But we will know the capability of the actuator.
Yes,
because the actuator may not support some things.
Yes. So when the orchestrator gets this schema, it is able to understand that, okay, this is for the stateless packet filtering, and it understands only these actions instead of 30 actions that are in the language. Yeah. Okay. And here is the mapping of one OpenC2 command to the Cisco iOS command in our particular case, and we have developed a library for Cisco access control list, which is a packet filtering tool from Cisco. But Cisco doesn't understand yet the OpenC2 language, so we had to develop a proxy, so-called proxy, but it's a tool. It's a software that translates OpenC2 commands to the Cisco. So as we can see on the slide, the action deny from OpenC2 is translated to deny to the Cisco, the first line here, and then the action allow from OpenC2 is translated to permit. So we have different languages now, and the other fields. For example, the protocol TCP is translated to TCP as well, and other fields. This example is about if we want to block an SSH access from certain group of hosts to a specific destination. Okay, here is only a piece of our code that we are developing. We are working hard now, and this piece of code is part of a validation process. After the orchestrator issues the command, our code is able to validate it if it is in conform with the OpenC2 language specification, and after the validation, it maps or it translates from OpenC2 to Cisco iOS language, as we have seen it. Okay, I have to bring back the architecture that Vasileios already discussed, because our case, our tool, is on the second case. Like it means we have an orchestrator, we have a proxy, OpenC2 proxy, and we have the consumer. In our case, it's a Cisco device. And I'm going to give you a brief overflow of one command from the orchestrator to the Cisco router. An orchestrator issues a command, OpenC2 command, and it sends to the OpenC2 proxy. In our case, the tool that we have developed, and the orchestrator says say to the OpenC2 proxy that I have, or we need to block this group of hosts to access the SSH connection or remote connection. And then the orchestrator sends the command to the proxy, and the proxy then has to do the translation from OpenC2 language to the Cisco iOS language. And then after it does the translation, it sends the command. Now the command from the OpenC2 proxy to the Cisco device is understandable by Cisco. So, and then if we go back from our OpenC2 command, we have requested some extra arguments. For example, we have the command ID to keep track of the command, and we have requested a response for just to check if the command that we have submitted is successfully applied. And then the proxy sends a response to the orchestrator, and then the orchestrator knows that the command was successfully applied. Yes, and OpenC2, as Vasileios said, it's an international initiative initiated by the NSA, but we are now a big community. For example, also a University of Oslo, or our group is involved, and there are many other big organizations, and you are welcome to join the community by visiting openc2.org or Oasis official sites.
So to summarize in 20 seconds. Okay, to summarize in 20 seconds. OpenC2 helps what? In incident response. Now the incident responder doesn't need to have great domain expertise of its technology. You can speak OpenC2 and you can communicate with any technology. Okay? And the most important thing is that machines can communicate with other machines, machine-to-machine communication. As I gave the example before, the sandbox now since it knows that this email is malicious, because we have cyber threat intelligence that the command and control server that communicate is malicious, okay, the IP is malicious, we know how it is, then the sandbox can push a firewall command to the firewall itself. This is the point. In cyber relevant time, immediately, in milliseconds. This is it. Thank you.
Thank you.